Welcome student to the another lecture of halogen derivatives. In last lecture we have started actually with alkene, and we have completed alkene of two type, right? One is symmetrical, other is unsymmetrical, and one more is left, that is alkene when treated in peroxide. It is also called as peroxide effect. It is also called as Karsh effect. It is also called as Karsh-Mayow effect. Okay, or it is also called as anti-Markovnikov rule. Anti-Markovnikov's rule, or it is also called as Karsh, K-H-A-R-A-S-C-H, Karsh effect or Karsh-Mayow effect. Okay, let's understand what is the reaction. Suppose I have unsymmetrical alkene like this, CH3, CH double bond CH2. This is unsymmetrical alkene. When this unsymmetrical alkane is treated with HBr, right? But if this reaction take place in presence of peroxide, like hydrogen peroxide, H2O2, or benzoyl peroxide, or any peroxide, then the product which is obtained is not according to the Markovnikov's rule, right? The product obtained is according to the anti-Markovnikov rule. What is the Markovnikov rule, student? In last lecture we have done. The rule says that when an unsymmetrical alkene is treated with unsymmetrical reagent, the negative part of the reagent will go to that carbon which contain less number of hydrogen, means Br is going to attach over here. So what will be anti-Markovnikov rule? In anti-Markovnikov rule, the negative part of the reagent will go to that carbon which contain more number of hydrogen. And I am talking about, see, you will feel like, so this carbon has more number of hydrogen, but we are talking about only those carbon which is unsaturated. That means I'm going to talk only about these two carbon. So in this two carbon, this carbon has more number of hydrogen, so this Br is going to attack over here, and obviously this H comes to this carbon, right? So the product will be CH3, CH2, CH2, Br. And student, very important point is this formed N-alkyl bromide. This is what? N-alkyl bromide, right? And in Markovnikov rule, we got iso alkyl bromide, and that's the difference, right? If question comes, how are you going to prepare CH3 CHBr CH3, then what will be using? I'll be using HBr, but I'll be using Markovnikov rule. But if I have told to find out this or to prepare this, then I'll be using same reactant, but I'll be use peroxide. So if peroxide, I will get this product. If I don't use peroxide, I'll get this product, right? Okay, so that was preparation number 4, and now we are moving to the last preparation, that is by halogen exchange. By halogen exchange, or I can say from alkyl halide. From alkyl halide, that means we are preparing alkyl halide from alkyl halide. Okay, right? Let's start. In that, the first reaction is called, Flinkstein reaction. Finkelstein reaction. This reaction is called as a Finkelstein reaction. I rewrite this. I think there's a mistake in the spelling. I write again. Finkelstein reaction. Okay. Now, what happened in this reaction? In this reaction, we prepare in Finkelstein reaction. We prepare alkyl iodide. We prepare what? Alkyl iodide from any alkyl halide. Normally, alkyl halide we take is what? RCl or RBr. So if I have this alkyl halide, if from this alkyl halide I prepare Ri, then it will be called as Finkelstein reaction. Okay, so let's start. I take alkyl chloride and I treat this with sodium iodide. I have to treat this with what? Sodium iodide, or I can also take potassium iodide. Okay, now, but normally we take sodium iodide. So alkyl chloride treated with sodium iodide in presence of dry acetone. Now this Cl will be replaced by this iodine and we get Ri plus what is left? NaCl, right? This reaction can also be carried out by RBr, NaI. This condition remains same and the product will be Ri plus NaBr. Okay, student. So when we get a product that is Ri either from RCl or RBr, then this reaction is called Finkelstein reaction. Clear, student? Okay. Now, moving to the another reaction in this same part. This is called Schwartz reaction. And what happened in Schwartz reaction? In Schwartz reaction, we form RF. What we form? RF. Right. Now, for example, I have CH3Cl. I have CH3Cl and I treat this with AgF, silver fluoride. If I treat this with AgF, it will happen like this. Chlorine will be replaced by fluorine and I will get CH3F plus AgCl. Right. Now student, instead of AgF, I can also use COF2. I can also use SbF3. I can also use Hg2F2. Right. I can use all these things while preparing alkyl fluoride. And these reactions will be termed as what? It will be termed as Schwartz reaction. Right? I can take chloride, I can take bromide, right? I can take iodide, and if I treat with this and if I get a product with alkyl fluoride, it will be termed as Schwartz reaction. Okay, so here we have completed preparation part. Now moving to the next topic, that is physical properties. Physical properties of alkyl halide. Okay, now as we know, the lower members of alkyl halide. Normally in alkanes we have studied lower members of alkane are gaseous, right? That is from carbon 1 to carbon 5. After that it becomes liquid till carbon 17, and from carbon 17 onwards it becomes solid. Same way, lower member of alkyl halide are gaseous, higher members are comparatively higher members are liquid, then further higher members are solid. That means alkyl halide exists in all the three forms, that is solid, liquid and gas. Okay, normally volatile halogen compounds have sweet smell. They have sweet smell, right? Now student, let's talk the important point of this, where actually we studied about its boiling point, melting point, points like that. Okay, so we'll be first dealing in that will be nature of intermolecular forces. Nature of intermolecular forces. Now student, let's first understand Rx. When I say Rx, okay, this is what? This is halogen. Halogens are electronegative. So when halogens are electronegative, it tends to pull the electron to itself. It pulls the electron to itself, it becomes partially negative and it becomes partially positive. That means alkyl halide is slightly, it's not very high, but is slightly polar in nature. Polar in nature. Right? Whereas if I compare this, see, if you have seen the first lecture, in that we have seen that is they are the derivative of alkene. That means the parent is alkene, right? They are made from alkene. When I compare with alkene, alkanes are non-polar. Alkanes are what? Non-polar. But alkyl halides are polar in nature, right? So when I talk about some intermolecular force of attraction, means attraction between two alkanes, attraction between two alkyl halide, then we do understand that alkyl halide intermolecular force of attraction will be greater than in comparison to alkene. Why? Because if there is a polarity, right, negative will attract positive, positive is going to attract negative. So that's why the polarity of Rx will be higher in comparison to RH. Okay, understood this? Right. Now, moving to the next and the very important point, bond length. Bond length, and I'm talking alkyl halide. Suppose I take RF, I have RCl, RBr and RI. Can you tell me the increasing or decreasing order of bond length? It's very simple. See, R is same for all. Suppose I take methyl, CH3F, I take CH3Cl, CH3Br, or I take CH3I. So the alkyl group is going to be same for all, right? Okay. That means the bond length which depends upon the halogen, and halogen is fluorine, chlorine, bromine, iodine, and we have studied this in periodic table as we move from top to the bottom, right? As we move from top to the bottom, size goes on increasing. What does it mean? It means that the bond length of this is going to be least because the size is small, right? Whereas the bond length, whereas the iodine size is big, so the bond length of CH3I will be highest. So talking about bond length, so this will be less at with the order. Okay, now if I talk about bond enthalpy, student, then in this what will the bond enthalpy? See, bond length and bond enthalpy. What is bond enthalpy? Suppose I want to break this bond, right? I want to break this bond, okay, or I want to break the force of attraction between two alkyl halide. Okay, so if I want to break this bond, the amount of energy that is required to break this bond is called as bond enthalpy. Now student, the bond length is less, So the bond is length is less, that means bond energy will be more. If bond is strong, that means more amount of energy required to break that bond, right? So this is least bond length, that means bond energy will be highest. So if I take CH3F, CH3Cl, CH3Br, CH3I, and if I talk about bond length, bond enthalpy, then bond enthalpy of this will be highest and CH3I will be least, right? Okay, and one more thing, student, and that's the important one, very important. What about dipole movement? Suppose I have CH3 in this only. I'm talking about dipole moment, student. Dipole moment. Okay. Now, suppose in CH3F, CH3Cl, CH3Br, and CH3I, which will have the highest dipole moment? Tell me. I give you one help, one hint. That atom which is more electronegative, they have the higher dipole moment. Okay, so more electronegative atom will have higher dipole moment. So if I go to according to that, that means fluorine will be the highest dipole moment, then comes CH3Cl, then comes CH3Br, then comes CH3I, right? But here there's a bit difference, student. That's why it's important. Here there's a bit difference. Why there's a difference, we have to understand. Exceptional case, this is an exceptional case, right? Now, why there's exceptionality, we have to understand. First, what is the difference? Let's understand. CH3Cl, this is the highest dipole moment. Then comes CH3F, then comes CH3Br, and then comes CH3I. That is how it goes. That means the difference lies over here. CH3Cl has a higher dipole moment in comparison to CH3F. The reason is that because you might have studied, see, when I say fluorine have lone pair of electrons, right? And these lone pair of electrons, they repel with each other, and that's the reason this happens. Okay, now moving to the next physical property. This is the important one, boiling point, student. Boiling point. Okay. Now, if I ask you the boiling point of alkane, if you compare between the boiling point of alkane and alkyl halide, which one will be the highest? Obviously, answer is alkyl halide will have a higher boiling point in comparison to alkane. This is because the force of attraction is greater. When there is a force of attraction higher, it will have higher boiling point because we require more amount of energy to break that. Now, suppose I take alkyl iode. If I take suppose Ri, Rpr, Rcl, Rf. Now tell me which will have highest boiling point. If I take alkyl halide, see, this was between alkane and alkyl halide, but if I have all alkyl halide and similar alkyl halide. Okay, example, if I take CH3I, CH3Br, CH3Cl, CH3F, right? Then in comparison, can you tell me which will have the highest boiling point? Okay, the highest boiling point will be this. It will be like this. Methyl iodide will have a higher boiling point in comparison to Br. This will have higher boiling point in comparison to Cl, in comparison to F. Now, obviously you have to understand. See, boiling point increases if molecular weight increases. Boiling point and molecular weight are directly proportional. If I take CH3 is same for all, but as we know, iodine has a higher molecular weight. So that's the reason the molecular boiling point of iodine will be greater than alkyl bromide, then alkyl chloride, then alkyl fluoride. Right? Now, but the question rises, suppose I take one more example. If I have similar type of halogen, example CH3Cl, C2H5Cl, C3H7Cl, C4H9Cl. Now, in this, all have same halogen, but you can see the carbon here's 1, here's 2, here's 3, here's 4. Means this will have highest molecular mass. So obviously the boiling point will be higher for this. So this will be the least one and this will be the highest one. Right? Clear? So if halogen is same, then the number of carbon, the one which have a higher number of carbon will have higher boiling point. Okay, student? Now, next one. What happens if I have isomeric halide? If I have isomeric halide. Isomeric halide. Right. Example. CH3, CH2, CH2, Br. CH3, CH, CH2 or CH3, here Br. Right? Okay. And or I increase one more. I increase one more carbon, CH3. I write here CH2. Okay, I want 4 carbon, right? So that I can take this also. CH3, 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 Br. Now, what we understand, this is 1 degree, this is 2 degree, and this is 3 degree alkyl halide. Now, in this case, student, tell me which will have higher boiling point. Right. See, here more branches is there. Right. So if the branches are more, then in that case, attraction will be less. When attraction will be less, then less amount of energy is required to break the bond. That means boiling point will be less. So 3 degree will have least boiling point, then 2 degree, then 1 degree. This is very important, student. Right. So as branching increases, what you have to understand? As branching increases, boiling point decreases. So branching and boiling point are inversely proportional. Got that? Okay. Now, moving to the next, that is solubility. Solubility of alkyl halide. Actually, alkyl halide is polar, and we also know what is also polar. What we have studied, like dissolve like. That means if a polar will be soluble in polar, non-polar will be soluble in non-polar solvent. That is what we have studied. But actually, alkyl halide is very least soluble in water. Obviously, the question arises why? Because water contain large amount of hydrogen bonding, right? If alkyl halide breaks that bond and if it forms a stronger bond, then the solubility obviously will be higher, but this does not happen. That's the reason alkyl halide is practically insoluble in water. It is not soluble in water. Okay, but it is soluble in non-polar organic solvent. It is soluble where? In non-polar organic solvent. Got that? Okay. Now, if I talk about aryl halide, student. If I talk about aryl halide, then aryl halide is also insoluble in water. It is not soluble in water. It is also insoluble in water, but soluble in organic solvent. It is soluble in organic solvent. Now in this one thing, student, we'll take one example for aryl halide. Okay, and we'll discuss boiling point as well as melting point for that. Okay, and most of the time this question comes in exam. All this structure is dichlorobenzene. Okay, but the difference is that this one is ortho dichlorobenzene, this one is ortho, this one is meta, and this one is para. That is where the difference lies. Right, now if I talk about boiling point, first I talk about boiling point. So whenever the question comes on that, understand if ortho is there, then ortho will always have higher boiling point. Ortho group will always have a higher boiling point in comparison to para, in comparison to meta. Right, ortho will have always higher boiling point in comparison to para, in comparison to meta. But when it comes to melting point, then para has a higher boiling point always, then in comparison to ortho, then in comparison to meta. Now if you think about melting point, see melting point, if a bond form is stronger, suppose I have a solid and the crystal lattice which is present is stronger, right? So then more amount of energy is required to break this. Okay, here this is symmetrical. Being symmetrical, the other molecules comes, they have a better way of forming a bond, right? So that's the reason they form better bonding in crystal lattice, right? The arrangement actually is better, and that's the reason the melting point is higher, right? Then comes ortho, and then comes meta. Remember this, student, this is the very important one. So we have completed the physical properties of alkyl halide. Okay, in next lecture we'll be starting with the chemical properties of alkyl halide. Okay, so for today we stop. Thank you.